I back again with part 3, which we are going to talk about the equipment specification in particular, and then I will give you an example, and hopefully this is going to be end of this lecture. So there are some highlighted parts in this diagram that basically points out the wide variety of terminology. You can see there's the accuracy here, there's a basically RMS, root mean square, has been used. There is the term DIN, which is the German national standards, which you might see it across the international standards, so it's good to know what does it mean. And then you can see standard deviation has been used, so accuracy, standard deviation, root mean square, so different termings. And you can see there's always a disclaimer that how they measure those accuracy under which conditions, so it can't be applicable for all conditions. So if you read the manufacturer specification, you always see that they're confused by the term of accuracy and precision. What they mention as accuracy in the manufacturer specification is actually precision of that instrument. So this is not right, what they're using. Precision is the right term for that. And to be honest, this is by itself is not in line with international standard and practice. So no matter how you try to be in line with the international standard requirement, you still see some discrepancy between the manufacturer specification and termings. But as far as you know, what can be the interpretation of those should be enough for us. Again, what manufacturer does to basically get the precision for the instrument, they follow the, do you remember I showed you there is a certain procedure for getting the precision for the instrument. We've talked about the total, but there is a list of them, so they will follow those procedures to get the precision for the equipment. But remember, they're very generic, they don't always reflect the general specific field conditions. As I said, they might be in the certain conditions, and to be honest, they're always better than what is actually happening or you can achieve using the instrument. So if they say 1 second for angle, don't really rely on them too much. So you might have different side condition or different measurement conditions, which basically gives you the different accuracy. So it is critical for us to follow equipment specification. What does it mean is we have to make sure that we can determine the traceability for the specification of the national, both national and international standards. If we say national or international, they're probably in line together. So if we follow one of, we can make sure that we can meet the other one. So we have to understand the standards and uncertainty, and we have to be aware of the condition of the testing which affect the final result. We have to be able to determine the correct confidence level which is stated for precision. Why I'm saying correct, you might say, yeah, I can read manufacturer specification, I can get the uncertainty for those measurements. Isn't it that one only? The answer is no. For example, if I'm saying the accuracy of horizontal reading is 1 second or 2 seconds, say. Good? This is pointing. This is when I'm reading one direction. Angle is usually 2 direction. So there are 2 of them involved. Yep. And remember we had this formula. Sorry, N is the number of observation. So, you know, if I'm repeating the measurement, do you remember, by n times, the final accuracy would be sigma multiplying root mean square of n, which is the number of observation. If I apply same rule to this one, I'm going to have 2 observation. Yep. So it's going to be 2 seconds squared of 2. This is the final accuracy that we can achieve for angle measurement. So just be careful about how you're interpreting the manufacturer specification. Again, we have to be aware of the condition, as I said, condition in which those accuracy has been tested. So in normal life, you're never going to have the ideal situations, so you always expect to have some less precision than what they are reporting in the manufacturer specification. Move on. So what we should do then, as a surveyor, we have to make sure that we are fit for purpose. What does it mean, fit for purpose? It means that we make sure that resources we have, equipments we have, procedure we are following, the computations we are doing, they meet the specifications, standard, and legislation as is expected for the specific project. So it's very important to follow that and trying to know what is actually wanted from us and what we can achieve using the different equipments. Like if you want to achieve, for example, the good height precision, say like 5 millimeter, do you use GNSS for that? I would say no. So this decision making is part of our surveying job, that we have to be aware and we have to complete it in a good manner, and otherwise you're going to mess up the whole project. You're going to spend lots of time going out there, do the job, can't get the required specification. And it's very critical even for bigger job like main road construction, is where the procedure and application and accuracy comes to effect. So I talked about the specification. I've mentioned that a couple of times, but I've never actually defined that. What is a specification? A specification is basically integral part of an organization standard operating procedure. So it gives you the procedure you have to follow to get that standards requirement. It is mainly affecting the big companies, as I said. Specification is very important for mining company, for example, for large construction firm. ITSM standards are adopted to show you what procedure you have to follow in order to achieve good position or certainty for control surveys, which you can go and read. And basically, a specification can be very general, just give you a general idea. It can be mid-level, which mostly giving you idea about the design parameter rather than the uncertainty. It can be very specific, which, as I said, for the bigger job we would expect, or legislation we would expect to have very perspective on. So the art of matching the specification to the resources available is something we are seeking for you guys as a surveyor to do. So you have to be able to see what are the equipments I have, or your available resources, like in terms of equipment, software, and what field procedure you need to follow to be able to achieve the certain accuracy for the certain projects. I told you it's going to be basic specification or general, very general. It can be mid-level and it can be very good one, the fully detailed one. So basic specification is pretty much this example. Is like if you have been asked to do the detailed survey, which basically collecting the feature, trainings, and existing infrastructure to provide the base for the design of the facility of a new park area that they want to construct. So you will be given survey and map of all existing feature, including the road center line, grade along the existing road from X to Y, and all those things. Do you think it's very specific about what you need to do? No, it's the general, very basic specification. What accuracy you need to achieve is your decision, basically based on your experience or based on your previous works you've done, and you know what sorts of accuracy you're looking for. So this is not what we want as a surveyor. We want to have more detailed one. It can be a mid-level, as I said, where the design criteria dominate the specification and accuracy specification are unclear. Why I'm saying unclear, I'm going to give you some example and show you what does it mean by unclear. So when I'm saying unclear, in terms of, they will give you some statement about the specification, which I found many of them in different documents, and then you will see it's not clear what, for example, confidence level they're talking about. You have to make a decision about how many points you have to do, what's the sufficient points. Whether when they say accuracy, does it really a standard deviation? What is root mean square error? So those things are different terminology that may confuse you in terms of a specification. Let's have a look at some of the unclear one. For example, this one is the specification for sending out the battle line using the RTK GPS. So if you read through, I'm not going to read it, obviously you can read it yourself, but I highlighted the part I want to show you. If you look at the red area, I'm talking about the accuracy of batter pegging is generally 0.2 meter horizontally and 0.1 meter vertically. When I'm saying the accuracy of batter is 0.2, 0.1, what is the confidence interval for it? Are we talking about the 68% or 95%? So it's not quite clear to me. Or another example is about the surface level for pavement. We have a sub-base base, and there's absolute and relative, which again we're not quite sure about that. And there is also not clear again what confidence level we're talking about when we're giving the tolerance. So this is not quite what we want. Again, it's not clear in terms of the specification. Another example you can see, these specs introduce percent relatively. So it says that more than 0.2% absolute. And I was like, it doesn't make sense what it wants to say. Again, we have the absolute tolerance. What does it mean by absolute? Does it mean 100%? Does it mean 99%? Does it mean 95? So it can be any of those. So which one is talking about? So it's not clear. It doesn't make sense. What it makes sense, again here you can see is the old-fashioned one, which we used to have the different classes of the accuracy we could achieve, and it given as a horizontal accuracy, vertical accuracy. Again, so what does it mean by accuracy here? Is it standard deviation? So it's more traditional approach of surveying. So, okay, I'll say, let's assume that accuracy is standard deviation and precision, which is always confusing. But I will say, okay, this is sigma. But if it's sigma, what I'm talking about, whether is it sigma or is it 2 sigma? Is it 68% or is it 95%? So which one is this one? I'm not sure, which is hugely different from each other. What is good, or what is the best specification that you can see is this one here. This is a more formal specification under legislation regulation. You can see it specifies everything quite clearly, which we call them highly perspective and detailed specification. Example of them can be seen in the state government agency when they deal with the major infrastructure, like as I said, road and transport. Here is main road, Department of Main Road. I don't know, in New South Wales RTA, if I'm right, or maybe they changed the name now. And there's a rail, for example, if it's like a mining company. So large engineering or surveying firms, they come with more and detailed specification. You've seen the term of tolerance is widely used in terms of surveying. We always say, what's the tolerance for that? But what I want to mention here is, try to not be confused the tolerance with the maximum permissible error. This is totally wrong. What tolerance gives you is the limit of rejection. If you have more than that, you have to redo the whole thing. It's not acceptable. So tolerance, you have to be aware that tolerance does not imply a level of uncertainty unless it's said in the specification, which most of the time it doesn't mean that. Good. So in this bit, I want to show you the example of setting up an abutment for bridge girders. So Let's have a look at this example and see what is the problem and how we're going to fix it. So if I want to read through the problem, is as we want to design, the design specification for girder installation are shown here. The surveyor planned to place the set out points for the abutment from the bridge survey control network. The distance between the abutment cannot be easily measured, so we can't really go and physically measure the distance between the abutments. So we want to know, if you look at the diagram, so we want to know how we would be able to measure it or set out, and what would be the uncertainty for measuring the distance of about the girder, which is 30 meters. Good. So let's have a look at this one. Assuming the distance between A and B, we say we can measure the distance from A to B directly. What are our options? First option is we set up our S1, station 1. We set A from station 1. Good. The next one is we set up in a station 2. We set out B from station 2. So A from station 1, B from station B. So if I'm removing that, what is the next option? Is if I set out A and B from one station, so it can be either from S1, so I'm setting out A and B from one station, or it can be from S2, both of them. And then I work it out the uncertainty in the distance, which is, we know from error propagation. Yep. So what's the third one? I'm trying to remove that. The third option is that, how about I set up these two from this station, and I set up both from the second station and evaluate the distance, uncertainty in the distance. So I set up both points from both stations. So there are three options that I can go. Let's have a look at the error analysis of these three options. I will show you the first method. You can find all the details in the study book, so I'm not going through the calc speed because we have the limited time in the lecture, but I will show you the first one just as an example. So if you want to set out, like, let's have a look at the first one. What's the first one? So I want to set out A from station 1 and B from station 2. Good. So what would be the uncertainties we have? So there's obviously there are some inputs is given in the study book that you can go and have a look, like the accuracy of the instrument. So there are some known elements like uncertainty in the setting out the instrument and set up the target. So if you look at those errors, we can sort it out, the errors or uncertainty for each position. So I can say the uncertainty for, let's come back here. I will look at the first method. Sorry, I don't know what's going on with that keyboard. So I'm trying to show you this one, A, and I'm setting up B from control station 2. Good. For the A, if I'm setting out, so there's some uncertainty in the positioning. So it can be the like sigma or S, because I put S because it's the limited number of observation. You can use the sigma. As I said, they're meaning differently, but interchangeable in some manners. In some places you can see they use sigma as S or the other way around. So there's always a ADM uncertainty with the measuring the distance. So we have the setup uncertainty for our instrument. Good. And then we have the setup uncertainty for target. And then we have another uncertainty, which is we're not sure whether this control station position is 100%. So there's no 100% confidence level. Yep. So there should be some error associated with that control station itself. So then I can say can be, if I assume the ADM for this, knowing the fact that this is, I'm trying to work it out, this is 60 meter, this is 30 meter, this is 60 meter. Good. Knowing to the fact that this is 60 meters, if the instrument accuracy is 2 millimeter plus 3 ppm, and we know we can times to 60, and then it gives us the accuracy, which is plus or minus 2.18. Good. So I can put 2.18 squared plus setup was half a meter, then target was half meter. Sorry, millimeter. I say meter. It's too much. Sorry, it's just me doing the mistakes. So this is millimeter, and these are all millimeter. And then we have the position accuracy for that is 1.5 millimeter. So the final result would be plus or minus 2.7 millimeter. Good. But you might say, hi Zara, yep, but this is for A, yep. How about B? B is pretty much the same. Right on this we have S2, which, assuming that the accuracy of control stations are the same, so it's going to give you the same answer. How we can get the accuracy of the distance is pretty simple. If you have the S for A, and then we have for B, can square them, and it's going to give you AB precision, which is going to be 2.7 squared plus 2.7 squared. But remember, when you are getting the results for that, which is plus or minus 3.8 millimeter, this is at 68% confidence level. To get it at to 95% confidence level, what we need to do? Times 2, which give you roughly 2, obviously it's 1.96. So it's going to give you 7.5 millimeter. So you can, similarly, you can calculate for sigma, sigma AB for the different method. And what I want to show you here is mostly, you can look at the calcs. We are not doing all the calcs here. Hopefully it gives you enough idea how you can calculate that. But we want to know that the specification, if I'm coming back here, they ask for the plus or minus 5 millimeter. My question is, can we meet that at 95 or either 95? This is for 99. Obviously you have to times to 2. I can't remember, 2.57 if I'm right. And then you can get this one here. So let's ignore the 99 at the moment and look at 95. Can I meet 5 millimeter? I would say method 3 marginal. But if I want to have 99% confidence level, no, there is no way I can meet that tolerance using these methods. So it's basically how you do the pre-analysis and making sure you can meet the standard requirements for setup, in this case, abutment. Yeah, but just imagine we can directly measure. If you want to directly measure, because you know the, we know that the accuracy of the instrument is 2 millimeter plus 3 ppm, so is plus or minus 2 millimeter plus 2, is that 2? Sorry, I'm trying to go back. 3 ppm, so it's going to be plus minus 2 millimeter plus 3 part per million times the distance was 30 meter, so it's 2.9, but remember this is at 68% confidence level. We have to double up. It's going to be roughly 4.3 millimeter at 95 confidence level, if I'm right. So similarly, you can get for other instrument, like if we are using the tape, if we are using the laser, just imagine you can get different accuracy. So obviously tape and laser giving you better uncertainty than EDM. But I want you to do an exercise this time, and just imagine you want to set out head walls this time. If you want to set out the head walls, we might need to introduce another error, which is the zenith angles errors, as well as the other errors we have with setting up the instrument, target, coordinates, and everything. We have to consider that one and then see whether we can achieve the required accuracy or not. So moving on, the next bit we want to talk about is as-built or compliance surveyor. We all know about the as-constructed as-built surveyor. Basically, this is the thing we are doing, or survey we are doing, to make sure that at the different stage of the construction project, to make sure that we are comply or conform to the design specification and standards. It's pretty much same. It's different terming, just as-built survey and as-constructed, they're pretty much the same. So it's basically to check that as constructors approve or meet the design specification. Why we need error analysis for this type of survey is very important. Basically, it's most of these surveys to make sure that you do the error analysis to make sure that you can meet the standard requirement. So first of all, we have to qualify the degree of fit between the design and as-built. Next, we have to determine the special requirement and make sure that the modeled specification is met by the required degree of precision. Like if you're setting out the road, maybe it's going to be the pavement surface departure from the design of grade and elevation. To ensure that the audit survey has enough precision, and we have to make sure that if you are doing audit survey, the argument is how precise is your audit. If you have any error in your audit, it's gonna affect the assessment you're doing. If it's not is worse than the required precision, it's really meaningless. So it doesn't make sense. So let's have a look at this scenario. Consider you have a set out of survey which has the few elements of uncertainty, as I say overall function can be your survey. We have number of uncertainty and can be expressed as the function of A, B, C to N. And then we assume that our audit survey also can be expressed as another function called G, which has the same terms. So we follow the same procedure, similar equipment, similar practice. So we would expect the difference shows us how good is our survey. But is this the case? No. The problem is how you're going to assess your sigma of difference. What sorts of tests can be used? Good. Let's look at the simple example. Say we want to do the audit survey for the pavement. If we know the pavement tolerance is 8 millimeter and the survey set out has the precision of 5 plus or minus 5 millimeter at 95% confidence level, and then we conduct the audit survey which form the same control stations. We occupy the same station, use the same techniques and equipment, and we're assuming that we have again the uncertainty of 5 millimeter. So even if the tolerance is assumed as 95% confidence level, then the audit precision can be given as this. This is the pavement tolerance, 5 mil of uncertainty of the set out. So it's going to give you the overall 11 millimeter at 95%. But then we should say, no, it's not compliant to the design or requirement. But imagine you have 2 millimeter error in your audit survey, then the accuracy or uncertainty is going to be less than 10 mil, which changed the whole story. So this is highlighting the difficulty in designing the audit survey, because if your audit survey is not good, which always you're going to have some uncertainty attached to your audit survey, it's going to affect the final results in terms of conforming to the accuracy which is required or not. In this slide, I want to show you there is a difference between the standard operation procedure and a specification. What is the difference? Standard operation procedures is it can be very detailed. It's not like a specification give you general procedure, but if you have operating procedure, it's going to have the field operation, data export and import, software you need to use, all those things is in operation procedure, which is different. Specification has the uncertainty as well as the field some procedure. As I said, it's not very detailed, but operation procedure, it gives you step by step of what you need to do. The example of a standard operation procedure can be seen here. As you can see, it shows you step by step, very detailed procedure that you have to carry out in this case. So operation procedure, as a professional surveyor, it's very important for you to have the good knowledge of error analysis and to be able to interpret whatever is written in the standard and requirement, and to be able to choose which method you want to do to use and which equipment you want to use to achieve that. But it's not only this. What I'm saying to my student, there's always a difference between the technician and graduate. The difference is no one really asks the technician to do the error analysis, and you might write this specification. But if you're a graduate, you might be asked to do this job, and one day I'm pretty sure you're going to appreciate this module that we have at the moment. I know it's too heavy at the moment, you might be upset, but believe me or not, you're going to appreciate that at some stage. So you have to understand the client perceives and understand the design parameters to start off. If you have been asked to basically do some job, to make sure that you fit for purpose, you have to first understand the parameters, design parameter. Then you make sure you understand or clearly understand the accuracy definition in terms of the confidence level, what confidence level, relative uncertainty, tolerance, everything. And then hopefully we can get the make sure that we understand the specification and to be able to interpret those in the to evaluate the final result we have to achieve. And then from that you have to working out from the whole to the part and try to minimize the blunder and systematic error. It's the same rule, always like that. And then try to use precise control to set out imprecise points, but not the reverse. Yep, this is very important. So it can be the reverse one. You might have the precise. So all work must be included independent checks. This is also very important. As a surveyor, we always need to do checks and checks and checks. So emphasize on checks. But is it? No. To me, the more important one is whatever happens, they're going to blame on you as the first person. So make sure that you document all of your work and have the record of every field notes and every drawing, plan, sketch that you have, because someday you're going to need them to prove that your work was traceable and you did everything you need to do, and you look at all the specification and accuracy, you did all the analysis and error assessment. So these are the documents you need to have, keep record of them. Another example I'm giving you here, and we're going to have more extended one for the tutorial, which is going to be the next week. is example of if you want to set out the bridge. It's very complicated. It's not really easy task, and you have to do lots of pre-analysis to make sure that you can achieve the certain accuracy which is required to setting out the bridge. If you look at this example, first of all, there is always a need for the bridge control line, which is in this case between 2 to 6. So why we need to have bridge control line is very simple, because we need to be able to check our accuracy. Usually what they do, they set out the bridge control line, and they at the end they can also measure that using independent measurement like a tape measure or something, and then they can compare it and see how good is your set out. It's basically used for the workers, for the inspector or workers, or even you to check your work. So the other points from we can see we have two PSM 1 and 2, and then we have the 1 to 10 bridge controls. So how we're going to design them is basically very complicated, so we have to know which area we want to put them. In reality, you try to be close to the main or critical structure that you have to set up. For example, here you see we have a roadway off ramp, and then we have roadway here, so we're going to have some marks here. There are some head walls and pylons that we have set out and check their control their accuracy. So we have to have basically different points here to check the accuracy of those setouts. But how are we going to make sure we can achieve the accuracy requirement for bridge setout? Bridge setout is very complex task, so it's not only one accuracy. You say, I want to achieve the accuracy of plus or minus 5 mil for the setout. It's not like that. We have to think critically. How we're going to think is easy. It might seem complex, but believe me, it's not that complex as you think. First of all, we have to do a planning analysis for precision needed in each area. Then we can run the pre-analysis of the network, and then finally we can compare the two. How we do the first step though? How you do the planning analysis of precision needed? So we identify the area, like the first area A is basically represent the road surveys for the approaches and off-ramp. You see, there's off-ramp, there's a roadway. Then there is a B section that has different accuracy, which is represent the major earthwork on the approaches. So they might have different accuracy or might require different accuracy. Then we have C, which is the bridge control line, which shows in terms of which needed in terms of alignment and distances. Accuracy requirement is very precise. And then we have D area, which is the head walls and pylons, where we want to have the basically girder installation plus final checking for all of those. Then we have A, B, C, D, and then the next one is the E, which basically represent the positional uncertainty. We all know positional uncertainty is in respect to the national system or national datum. Then we have F, which shows the survey uncertainty, which is within the bridge control network. And then we have G area, which is here. Good. G area is the control area for pies, pylon, and cross-section abandonment control. So what I mean, obviously you don't need to remember all of those, but if you have been given tasks like that, you have to sit down and think, where is my earthwork, major earthwork, okay, A and B. What are the accuracy requirements for them? How am I going to check my head walls and pylons or pies? Where I need to have the control marks for them? What's the accuracy I have to achieve for that particular control marks or particular area? What's the accuracy I need to achieve, for example, for bridge control lines in terms of alignment and distance, length and direction, basically. All those things should be think through. Once you decide, you can just prepare the plan like this with a rough positions of the points you want to set out. Obviously, you can also get the you can also do the pre-survey and get some position for them, and then come back in the office. You have to remember, planning should allow you to design a network like this, and then you might need to repeat it many times to get the ideal position for all those points, as well as the required accuracy that you need to achieve. You also need to think about the optical location of a secondary control and recovery stations that also you need to assess. The other thing you have to think, if you need to remove or move some of these control points due to the earthwork or something. For example, I put up this one, number 2, but as we are constructing the road or off-ramp, I might not be able to use it for the whole project. I might think to whether I need to move it or not. So you have to think about all of those in the planning stage. So nowadays there is an emphasis to have more quality assurance and quality control in surveying. So the organization, they need to make sure that they have to show that they're monitoring and that they monitor the procedure and the measurement equipment. They conform the standard requirement in the field. So there's a quality assurance and quality control need for the survey job. They have to basically ensure that they have a valid results in terms of the measurement equipment. They probably need to calibrate their measurements or verify them to the national or international level. If they are not available, they probably need to record it for the future use. Make sure that if it's not within calibration, you probably need to adjust or readjust as necessary. Then have identification in order to determine its calibration status, and for later on or for future reference. Make sure that this about the adjustment, because they probably could invalidate the measurement results. So be aware of that, and then try to protect your instrument to be damaged while you are transporting or storing them in the storeroom or handling. So those things, if you have any damage, it's going to affect the final results or final accuracy that you can achieve, obviously. So as a professional surveyor, to finalize, or these are the final slides, obviously, we would expect you to fully understand the calibration and traceability and how you can interpret the results from the specification and regulation, if you need to read through and make sure that you meet those requirements and standards. You have to be able to calibrate and maintain all equipment and try to have document chain of evidence for the legal traceability. And then again, you have to make sure that there are always environmental factors. So whatever you see in the manufacturer specification is not what's happening in normal life. So you might have different environment which affects the final results that you can achieve. Be able to interpret the accuracy, precision, confidence level, all those terms from the specification, and try to see whether which surveying basically whether it's accepted to use a specific surveying equipment or standards, in terms of, for example, if you want to use GNSS to get a high precision in heighting, whether it's possible or not. So you should be able to interpret those and make a decision. Again, make sure that you understand error propagation theory that we had in module 1, and to be able to document how the survey and computation can meet the specification. Again, be aware of the relative and absolute uncertainty and application in a specific project. So we've seen a few examples. We're going to have more examples in the study book. I really want you to go and read and make sure that you understand those examples, because we can't really cover everything in the lecture. Hopefully I'm trying to cover it as much as I can in the tutorials and my lecture, but we would expect you to go and read the study book as well. So again, to me as a surveyor, you should be able to carry out the least square analysis for control surveys, understand what are the inputs, how you can test them, how you can change the design, or change how you measure, for example, the distance. Can you measure it in 2 ways, make it more precise, or can I read the angles face left, face right, get a more precise measurement? So these things are consideration. You have to be aware of that, and you should be able to do pre-analysis in least square adjustment. Again, I told you I'm gonna have the whole tutorial on the bridge control survey for next week, so hopefully you will learn more. In summary, to me, you should be able to understand the standard requirement and specification, and make sure that you know what is the best practice, how you can achieve it, and more importantly, how you can prove it. So document everything, guys. You should be proved that when you are doing construction work, like a road type of job, which is a very big project, you're always going to have the inspector which comes to the survey, and sometimes they have the as-built survey or audit survey as part of the construction, or sometimes they are doing as a separate survey. So inspector will come and they will check your final work, or as constructed, it might be in different stage of the project, and check your work against the model or design or standard requirements, and they want to see whether you met them or not. You have to be able to prove that you follow the procedure, you could meet the accuracy requirement, and you can prove it if it's required. So this is quote of the day. You better understand error analysis, because if you don't, if you're lucky, hope you're lucky and you don't have any errors, everything is alright. But if you don't, and if you're not lucky like me, then you might need to understand the uncertainty as you can qualify your work, your project, your measurements, your answers. So it's very important for us to understand error analysis, guys. Thank you for listening to me, and this is the end of lecture 2.